In this video, I'll show you how to study symmetry using this website, symorder.org, SYMOTTER.org. Symorder stands for Symmetry at Autoby. We will use its tutorial, gallery, and challenge. First, tutorial. And then we can see there are 5 different operations. Identity, that means doing nothing. Reflection, with respect to a symmetry plan. Inversion, with respect to a inversion center. Proper rotation, that's a rotation about a rotation axis. Improper rotation consists of 2 operations. First, rotation, and then second, reflection. So let's look at these symmetry elements and operations. There's nothing to talk about the identity operation because you just do nothing. How about symmetry plan? The corresponding operation is reflection through the plan. The symbol is sigma. Inversion center has, of course, a corresponding inversion operation. So every single point has a coordinates x, y, and z. You just need to change their signs to negative x, negative y, negative z. The symbol for inversion center is I. Proper axis with a symbol c sub n. This means we rotate about this axis by 360 divided by n degrees. If you have c sub 5, that means you rotate by 72 degrees. Improper rotation consists of 2 operations, rotation and then reflection. If you have, for example, a S6 symmetry element, for example in ethane, you rotate the molecule about the S6 improper axis by 60 degrees and then do a reflection through the plane that's perpendicular to the rotation axis. So I'm going to show you those molecules. First, I want to show you this water as an example. Water belongs to the C2V point group. This C2V point group has 4 symmetry operations. First, the identity operation or symmetry element. This means doing nothing. The symbol is uppercase E. And we have C2 rotation. So I'm going to show you the C2 axis by checking this box. Alright, so this C2 axis. And then I'm going to show you how to rotate it about the C2 axis by 180 degrees. And then there are 2 symmetry planes, sigma xz and sigma yz. These 2 symmetry planes both contain the principal axis. So I'm going to show you these 2 symmetry planes. Alright, they both contain the principal axis. These 2 are sigma v's. V stands for vertical. Alright, and then let's do one of the reflection operation. The oxygen atom did not move because this symmetry plane contains the oxygen atom. Now how about this reflection? It's going to do nothing to the 3 atoms because this symmetry plane contains all 3 atoms. But anyway, let's do it. Nothing happened. Now let's look at benzene. Benzene belongs to the D6H point group. There are 24 operations. Therefore, the order of this point group is 24. What does this D6H mean? So 6 means the principal axis is C6. H means there's a sigma H symmetry plane H stands for horizontal. This sigma H symmetry plane is perpendicular to the principal C6 axis. So I'm going to show you the C6 principal axis first, and then I'm going to show you the sigma H symmetry plane. So again, H stands for horizontal. This plane is perpendicular to the principal axis. Alright, and then whenever you see this D, that means there are sigma D's, so you can look for sigma D's. And also, you can look for C2 axis that are perpendicular to the principal axis as well. So I'm going to show you that there are 6 C2 axes all perpendicular to the principal axis. Alright, so now let's look at some of the symmetry operations. Let's look at the principal rotation axis first. We're going to rotate. You can rotate 60 degrees or negative 60 degrees. So there are two different operations here. This is 60 degrees. This is negative 60 degrees. Alright. There are two C3 rotations, only because you can rotate 120 degrees or negative 120 degrees. So let's do 120, negative 120. Whether it's clockwise or counterclockwise doesn't really matter. This is clockwise. Again, you can see this clockwise. But if I look at the benzene the other way, it's counterclockwise, so it doesn't really matter. C2 rotation. So this C2 rotation is actually the C6 rotation 3 times. Right, so I'm going to play this 120 degrees. I want to show you this C2 axis is the same as the C6 axis. Alright, it's just if you do C6 3 times, it's going to be 180 degrees. So 180 degrees. Alright, and then there are two different types of C2 prime rotations. This is C2 prime, this is C2 double prime. What's the difference? Well, C2 prime, you can look at this. C2 prime, they cross the carbon atoms. C2 double prime, they will cross the center of the bonds. So you get 3 more C2. There's a trick. If the principal axis is C6, and then somehow you find one C2 axis that's perpendicular to the principal C6, and then you will have 5 more C2 axes. So in sum, you just have 6 C2 axes perpendicular to the principal C6 axis. You are not going to find 3 or 4 or 5 or 7. It's going to be just exactly 6 C2 axis perpendicular to the principal C6. Alright, let's look at one more. How about S3 rotation? So from this symbol, we know it's going to rotate 120 degrees followed by a reflection. So I'm going to show you the S3 axis here and the symmetry plane that's perpendicular to this S3. So basically this hydrogen atom will rotate 120 degrees to here, and then a reflection is going to do nothing to the position of that hydrogen because this symmetry plane contains all those atoms. But anyway, let's do it. Rotate, reflect. Let me show you S6. We're going to rotate 60 degrees followed by a reflection, 60 degrees, and then reflection. Again, there is a reflection, but that doesn't change the positions of any of those atoms because this symmetry plane contains all 12 atoms. Now let's look at this sigma H. The operation does not change the positions. Again, this sigma H contains all those atoms. Sigma D's and sigma V's all contain this principal C6 symmetry element. So I want to show you the C6 here. This D stands for dihedral dissect, V stands for vertical. So this sigma D's, I think, contains all the some of the C2 axis, and they also contain this principal C6 axis. Sigma V's also contain the principal axis, but what's the difference between sigma D and sigma V? You're gonna see this sigma V's are containing the carbon and hydrogen atoms. So you have a total of 6 symmetry planes that contain the principal axis. Now let's look at ethane. It's a little bit complicated. Ethane has a D3D point group for its more stable staggered configuration. If you have a eclipsed configuration, I think the point group is D3H with a sigma H plane, C3 principal axis, and 3 C2 axis that are perpendicular to the C3. But anyway, let's get back to this staggered configuration, and then let's look at some symmetry operations. C3, we can easily see C3 going through these 2 carbon atoms, and then let's do a rotation. How about C2? There are 3 C2 axes. These are not obvious, but I want to show you this 3 C2 axes are all perpendicular to the principal axis. 1, 2, 3. So if you have N C2 axis perpendicular to the Cm principal axis, you know the point group is going to be a uppercase D. Okay, so it's going to be Dn at least. It can be Dn, Dnd, or Dnh. So it can be, in this case, if you have a C3 principal axis and 3 C2 axis perpendicular to C3, and then you will either have D3 or D3D or D3H. And then if you have sigma symmetry planes that contain the principal axis, it's going to be D3D. If you have a symmetry plane perpendicular to the principal axis, it's going to be D3H. Otherwise, it's D3. So I'm going to show you the sigma H here. Oh, sigma D here. There are 3 of those. 1, 2, 3. And you can tell that this 3 sigma D's contain the principal axis. Therefore, it's a D3D point group. What's more interesting is the improper rotation. So I'm going to show you this S6 rotation. This hydrogen atom is going to be here after a rotation by 60 degrees and followed by a reflection. So let's do it. Rotation, reflection. All right, a different angle. We're going to see the rotation and the reflection. Rotation, now reflection. Okay, that's S6. Finally, let's look at methane. Methane has a TD point group. Very high symmetry. Again, 24 operations. So if you have 24 symmetry operations, including the identity operation, and we say the order of the point group is 24. All right, so there are 8 C3 rotations. Why 8? It's kind of strange. But you can see there are 4 CH bonds. So you have 4 C3 axes. And then for each C3 axis, there are 2 different operations. You can rotate this 120 degrees or negative 120 degrees. So I'm going to show you maybe just the one C3, and then we're going to do rotation, another rotation. Oh, this is a different one. Okay. All right, so that's C3 rotation. There are 3 C2 rotations. It's a bit difficult to visualize, but if I put it this way, you can see. Just imagine a C2 axis perpendicular to your screen. All right, and then let's do rotation here. Okay. Let's do a rotation. Okay. 180 degrees. There are 3 of them. They are all perpendicular to each other. Now let's look at the S4 improper rotation. That means we rotate 90 degrees followed by reflection. So again, we have to kind of just, let me show you one of the C2 axes first. And then we will rotate and reflect. Rotate, reflect. A different angle here. Again, we're going to rotate and followed by reflection. Rotation, 90 degrees, reflection. Okay. There are sigma D's. Because we have how many C2s? A bunch of 3 C2s. So you're gonna see there will be 3 sigma D's that contain the C2 rotation axis, and 3 sigma D's that bisect the C2 axis. So this one contains the C2 axis. I want you to imagine a C2 axis perpendicular to the screen and passes through this carbon. And this sigma D contains that C2 axis. All right, and also you can see each of the sigma D axis contain 1 carbon and 2 hydrogen atoms. Now we're gonna look at 3 others. Okay, it looks a bit complicated, so I'm gonna get rid of 5 of those. So this one, let's look at this one here. It contains this carbon and this 2 hydrogen atom. It contains this carbon and 2 other hydrogen atom. Okay, now this 2 hydrogen atoms. Now why 6? Let's label the 4 hydrogen atoms A, B, C, and D. So the sigma D plane must contain 2 hydrogen atoms. So it can be AB, AC, AD, or BC, BD, or CD. So there are 6 possible combinations there. Alright, so this is methane with a tetrahedral point group with 24 symmetry operations, thus an order of 24. Now let's look at one of the gallery problem. This is Allene, CH2, CCH2. The point group is D to D. You can see here there are 8 different symmetry operations. Thus, this D to D point group has an order of 8. Now let's look at some of the symmetry operations. Identity means doing nothing. We don't care about this. And then as for rotation, let's rotate this 90 degrees followed by a reflection. There are 2 as for rotations because you can rotate 90 degrees or negative 90 degrees. So let me show you the S4 axis and the symmetry plane that's perpendicular to S4. Now let's gonna do rotation followed by reflection. Rotate, now reflect. Okay, and then rotate in the opposite direction, and then reflect. Of course, there are C2 rotations. That's it, 180 degrees. And then there are two C2 prime rotations. These two are perpendicular to C2. Okay, the two C2 prime axes are perpendicular to the C2. So one here, the other one here. So I'm gonna, let's see, I'm gonna show you this two. These two are C2 primes. They are perpendicular to this principal C2. I'm gonna click this principal C2 here. So this is a principal and then two C2 prime. All right, and then we're gonna do some operations. Let's see, what's the best way to visualize this? Maybe this way. Okay. The other C2 prime. All right, and sigma D's. These two sigma D's contain the principal C2 axis. Let's do one reflection. So this hydrogen goes here, this hydrogen goes here. The other four atoms, two carbon, these two hydrogen atoms are on this symmetry plane, therefore there's no effect. Let's do this again. Reflection of these two hydrogen atoms. All right, and then this is a D2D point groups. D2D point groups first contain a C2 principal axis. This D means there are two sigma D's. This uppercase D, the first letter D, uppercase D, means there are two C2 axis perpendicular to the principal C2 axis. Again, if you look at a point group, that's either DN or DNH or DND. That means there's a C sub n principal axis, and there are n C2 axis perpendicular to the principal axis. And then if you have additional symmetry planes, you need to look at the symmetry plane and tell if this symmetry plane is perpendicular to the principal axis or contain the principal axis. If the symmetry plane is perpendicular to the principal axis, we say that's sigma H and you have DNH. If the symmetry plane contains the principal axis, and then you're going to have n of those, and we say this is going to be DND point group. So this is the gallery, and you can see there are many of those molecules. You can take a look. This is D5D. Maybe we can take a look at D5D. Again, there's a C5 principal axis. That's what this 5 means. And once you see this uppercase D, the first letter, uppercase D, that means there are 5 C2 rotational axis, and all of them are perpendicular to the principal axis. So I want to show you this 5 C2 axis. I want to show you the principal C5 axis. So you can see there's a C5 and there are 5 C2s perpendicular to the principal axis. All right, so, and then the last D means you have sigma D's that contain the principal axis. 5 of them. So I'll click this to show you the 5 sigma D's. They all contain the principal axis. Now finally, the challenge. So this will guide you through the determination of the point group. So I'm going to show you a fairly complicated example, cyclohexane. During my PhD dissertation defense, one of the committee members asked me what's the point group of this. All right, first, I want you to just look at this molecule and take a guess about the point group. It's fairly complicated. But first, you can easily see there's a C3 axis because you can rotate this molecule. about the axis that's perpendicular to the screen, right? So this atom will go here, this atom will go here, all right? So again, now you're looking at a C3 axis here. But then it's a little bit hard for you to probably imagine there are 3 C2 axes perpendicular to this principal axis. So it's going to be at least a D3 point group. On top of that, there are 3 sigma Ds that contain the principal axis. So probably you can imagine we can just cut it this way. This symmetry plan, imagine there's a plan. We're cutting the screen this way, or this way, or this way. So in the end, you're gonna see it's a D3D point group. But let's look at the questions and answer them one by one. Does this molecule have an infinite rotation axis? C infinity. No, obviously not. But if you have a linear molecule, then yes, a linear molecule contains C infinity. So let's click yes first. Okay. Does this molecule contain inversion center? If you have a, let's say, homonuclear molecule, H2, yes. And then it's going to be D infinite H. Okay, so H2, O2, Cl2, those are D infinite H. Also, CO2 has a D infinite H group, CO2 with the inversion center at the carbon atom. But if you check the answer, it's going to tell you it's wrong. So, okay. Oh, actually, this is correct. This answer is correct. It does contain an inversion center. Let's get back to this challenge. Cyclohexane. Okay, obviously there's no infinite rotation axis. Again, you only observe C infinity for linear molecules, so I'm going to click no. Does this molecule contain 2 or more unique C3? So I can see 1. So again, perpendicular to the screen. But there's only 1, so I'm going to answer no. What if you have 2 or more unique C3? Then congratulations, you're going to get a point group with very high symmetry. So, but not this case. Okay, so I'm going to say no. Select the highest order proper rotation axis. It's going to be C3, 1, 2, 3. Okay, 1, 2, 3. All right, this 300 atoms. If you look at this 1, 2, 3, 300 atoms, and imagine there's a rotation axis in the middle. So I'm going to say 3. Are there 3 C2 axes perpendicular to the highest order axis? Okay, this is the hard part. Yes, there are. So I don't know. Let's see. Let's see if I can show you this. I'm gonna ask you to imagine there's a C2 axis perpendicular to the screen. Okay, going through the center of this carbon-carbon bond and this carbon-carbon bond, so that when we rotate this molecule about this axis, this carbon will go here, this hydrogen will go here, this hydrogen will go here, this hydrogen will go here, and this carbon will go here. This carbon on the back will go here, right? So it's going to do a rotation. So this is the one of the 3 C2 axes. What about the other 2? Again, you just need to imagine, you need to find 2 carbon-carbon bonds opposite to each other. Find their centers and then draw a line to connect the 2 centers, and then you will get a C2 axis. So again, if you look at this carbon-carbon bond, this carbon-carbon bond, find the center here, find another center here, draw a line here. That's another C2. The third C2 is between the center of this carbon-carbon bond and the center of the other carbon-carbon bond. So I'm going to click yes. Does this molecule contain a horizontal reflection plane perpendicular to the, okay, this is the C3 principal axis. And do you see a sigma H perpendicular to this? No, because this is sigma H, and then if there's one, but I don't see 300 atoms on here, here, and here. So let's say no. Does this molecule contain 3 dihedral reflection planes? Yes, dihedral reflection planes contain the C3 axis. Again, the C3 is perpendicular to the screen. So this is your C3. Okay, over here, this C3 axis is perpendicular to the computer screen. And then you have 1 sigma D that contain these 2 carbon atoms. Oh, I'm sorry, 1 sigma D that contains this hydrogen, this carbon, and the center of the molecule. 1, 2, 3, 3 points can define a plane. 1, 2, 3. And then this hydrogen will be reflected to here. This hydrogen will be reflected to here. So again, we have 1 symmetry plane, 2 symmetry plane, and 3 symmetry planes. All of the 3 symmetry planes contain the principal axis. So I'm going to say yes. All right. You determine the point group is D3D. So check answers. Yes. It's all correct, and then we can show the C3 axis. Okay, so this is C3 axis, and I want you to see the 3C2 axis here. Okay, they are all perpendicular to the C3, and this C2 crosses the center of this carbon-carbon bond and the center of the opposite carbon-carbon bond. All right, and then I want to show you the sigma D's as well. Of them contains the C3 principal axis. Okay, 1, 2, 3, 3 planes. All right, now we're done with this challenge. I want to show you the eclipsed ethane molecule. It's a very interesting molecule. So ethane. Oh, unfortunately, they don't have this eclipsed ethane. So I'll just give you another example. Ammonia. It's pretty simple. You can walk it through by answering those questions, but again, it's not linear. Therefore, there's no infinite rotation axis. And actually, you can just immediately see there's a C3. There are 3 sigma V's that contain the C3. There's no horizontal sigma H. Therefore, it's simply C3V. C3V. Okay? C3 axis. 3 sigma V's. 1, 2, 3 sigma V's. And also, there's a identity operation. So let's do it quickly. No. 2 or more C3, you have to say no, because we have only 1. All right, 3, select. 3C2, no. Contain a horizontal, no. Sigma V's, yes. There are 3 sigma V's. All of them contain the C3, so yes. Okay, C3V, check answer. So we got everything here. Over here, again, does this molecule contain 2 or more unique C3? Okay. I'm not sure about this. I think there's only 1 C3. And I'm guessing this is, I think this is wrong. There's only 1 C3 axis. There are 2 C3 operations, 120 degrees or negative 120 degrees, but there is only 1 unique C3 axis. So there's a mistake here with this challenge molecule. I think I'm going to report this error to the manager of the website. And again, we can do a play. Okay, it's just rotation. So again, this is wrong. This molecule contains 2 unique C3 axes. This is just wrong. This molecule contains only 1 unique C3 axis, and it's displayed right now over here. It's being displayed right now. All right.